Hello everyone, this is Sir Aris. Today let us talk about the curl and Stokes theorem. Suppose a rigid body is rotating with constant angular velocity omega. Omega is a vector along the axis of rotation, and the absolute value of omega is the magnitude of the angular velocity. The velocity of a particle in the rigid body is given by v equals omega cross product r, where r is the radius vector from a point in the rotation axis of to the particle. To better visualize this one, suppose this is the object. This object at a certain axis, it's rotating with an angular velocity omega. So if you want to pick, let's say, a point here, point P, the object relative to this, this is the axis, is at a distance r. This is the rotation axis of rotation. This is a point P. So the velocity of a particle, let's say if it's rotating counterclockwise, then it would be perpendicular. Let's say that is our V. Let us try to calculate del cross V, or the curl of V. So curl of V is simply the curl of V is omega cross R. Recall that we have A cross B cross C. So this is equal to a term proportional to B and C. So the ones in the parenthesis. So there's a term B, and it's a linear combination of a term proportional to B and a term proportional to C. So B and C. So the proportionality constant is, so here you have the dot product of the terms that are not included in of course for each of the two terms. So here you have B, so the remaining ones are A and C. So we dot product, we get the dot product of A dot C. Similarly for C, you have A dot B. Okay, and there is a negative sign. So I've written it like this, not in the back cab rule sequence, because I want to write this A on the leftmost side, because in comparison to this del operator is our A. So this is a derivative, which means that we cannot just put this directly in between or at the end, because this will act on either of omega and or r. In our case, let's set omega as constant so that when we take the derivative, it doesn't change. So if you take the derivative of this product, the derivative only acts on r. So here our del cross V would become, so we have del dot C, C is r, times B, which is omega, minus A dot B is del dot omega times r. Okay, so let's solve each one of these two terms individually. Del dot r, so this is partial respect to x. R is x, y, z, so x plus partial respect to y, y, partial respect to z, z. So partial of x with respect to x is 1. So you have 1. This is also 1. This one is 1. 1 plus 1 plus 1. That's equal to 3. So that would be 3 omega. How about this one? Del dot omega. Del dot omega, you have partial respect to x of omega x plus partial respect to y of omega y, partial respect to z of omega z. In full, you have del dot omega times r, that would be, so here, omega x, omega y, omega z, they are constants and they don't change if we take, they are zero if we take the derivative. So they are unchanged if we take the derivative of this times a, let's say r. So you have, we can write this as omega x partial respect to x plus omega y partial respect to y plus omega z partial respect to z. So here you have x plus y, so I hat, j hat plus z. So for this term here, if this acts on this, the derivative of this respect to x and this are both 0. So we are only left with this. So you have omega x partial respect to x of x. So that's 1. We're left with I. Similarly here, this becomes 0. This becomes 1. This becomes 0. So you have omega y j, and this one omega z k, which is just omega. Okay, so that our del cross v is del dot r, which is 3 omega, minus del dot omega r, so that is omega, 2 omega, or omega is 1/2 of del cross v. And what would it tell us? Angular velocity omega is proportional to the curl of v. So whenever we see curl, it means that it's something related to the angular velocity, something related to rotation. Here, in the simple case, del cross v gave the angular velocity. In other cases, for example, flow of fluid, the value of del cross v at a point is a measure of the angular velocity of the fluid in the neighborhood of the point. When del cross v, the curl of v is 0, in some region, v is called irrotational in that region. Consider a vector field v, capital letter V. For example, for water, that's velocity times the density rho. We define the circulation as the line integral around a closed plane curve. Given a point P and a direction N, let us find the component del cross V in the direction N at P. So we draw P along XY plane, choose N parallel to K. So suppose this is our XY coordinate system. This is our P. So P is along this plane, and we want to determine the circulation over around a closed path. Suppose this is our closed path. Okay, where the length here is dx, the length here is dy, and a path such that if we go around, so we choose this path, when we go around and we take that, we try to curl our right hand around the direction of the circulation, our thumb should point in the direction of N. Here, N is in the direction of K. K is parallel to XY, so XY, Z would be outside, so it's going outside. So if this is our Z, that is our N. So we curl around this using our right hand, the thumb directs towards this N hat, or parallel to K, towards K. So we want to find the circulation around an element of area d sigma centered on P using Stokes' theorem in 2 dimensions. We have this equation that K here, K is proportional to N, so we substitute. So you have here, our circulation that we define like this is equal to a curl over surface area. So from a line integral, we converted it to area integral. So assuming that the components of V have continuous first derivatives, then del cross V is continuous. In this case, the value of del cross V dot N over d sigma is nearly the same as it's nearly the same as del cross v dot n at p. So here with this d sigma is dx times dy. So that d sigma times the value of this would be proportional to this integral here. So we are not proportional, but they are approximately equal to each other. So here we approximate this as just this value at P, at point P, times the area. Okay, if we divide by d sigma and take the limit as d sigma approaching 0, we have that this del cross v dot n equals, take the limit as d sigma approaching 0 and the line integral here. Basically telling us that we can define our curl and its component towards the direction of n as a limit of this expression. Now consider a surface with area sigma divided into area elements d sigma by a network of curves. So suppose this is our curve, kind of curved, so that if we divide this into many areas, let's say we'll call this d sigma 1, d sigma 2, d sigma 3, and so on. On each area element, there is a specific direction for circulation. So we choose it so that for a chosen unit vector n perpendicular to each area element, for example, here you have n1, here n2, here you have n3. They're perpendicular to the surface, and all for all small elements here, the direction of n's should be on the same side of the surface. And the direction of circulation is such that, again, when our thumb is in the direction of right hand thumb is in the direction of n, the way our fingers curl, that would be the direction of our circulation, like this. Okay. Oops. And here you have, again, counterclockwise. Do the same thing for the others. For each area element, we have our Stokes theorem into dimensions v dot dr around d sigma is equal to, so integral, close integral, equals the surface integral of del cross v dot n. So for each, for the sum, to take the total, we sum all of our, so this for each area element. We sum all, that would be for the total surface area, and we do the same for this. So we simply add here, it becomes surface, the total area sigma, not only the d sigmas. Here we sum over all the sigmas. Now when we sum, this term, the line integral here would cancel with the line integral here. The line integral here would cancel here. This would cancel. This would cancel. Which means that all interior lines will have their line integrals canceled. What are left would be the circulations on the edges or the boundary. So we then, if we sum them all, you have curve bounding sigma. So the boundary only, we exclude, we don't include a sum of the interior parts because they just cancel. And here we take surface sigma. And this is Stokes' theorem. Okay. For by the way, difference between this and this d sigma here is that this is only for a small area element, whereas here, even if we apply it to a bigger surface, that equation still works. Recall that, as I have mentioned earlier, a vector field V is called irrotational, or conservative. It's also called lamellar, if del cross V equals 0. In this case, the gradient of a scalar function W could be written equal to V. So V can be written as a gradient of some scalar function that we call a scalar potential. If del dot V is 0, the vector field is called solenoidal. In this case, we can write V as a curl of a vector A. A is a vector function called the vector potential. We can prove that if V equals del cross A, then del dot V equals 0. We can also construct an A so that V equals del cross A if we know that del dot V equals 0. That is, so if we know del dot V equals 0, then we construct A. Here, we have an A that gives us, we take del cross V, then del dot V equals 0. So for example, we suppose you have a V. We want to find A such that V equals del cross A. First step, we want to know if we can really construct, we can really find an A such that V is del cross A. That would happen if del dot V equals 0. So it is possible to construct an A so that this expression is followed if del dot V equals 0. Let's find del dot V. So del dot V would be partial with respect to x of x squared minus y squared, or to be complete, let me write it as Vx, partial with respect to y, Vy, partial with respect to z, Vz. Vx is this, so let me write it as partial derivative of x, but let me solve the partial derivative directly. So partial derivative of this with respect to x, that's 2x. Okay, partial derivative of this with respect to y, that's 2z. Partial respect to z of this, that's 2z minus 2x. This 2x and 2x cancels, 2z cancels. This is 0, which means that we can find A because we know that del dot V equals 0, such that V equals del cross A. So we are looking for A such that V equals del cross A. This del cross A is the determinant of I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, ax, ay, az. Okay, and this v, we know that it's this. If you want to write, so this is equal to I x squared minus y squared minus j 2yz plus k, let me write it here, plus k z squared minus 2zx, z squared minus 2zx. Okay. Now del cross A, we simply expand this. Okay. So it would be difficult to find an expression generally for ax, ay, az, but A, there would be a lot of values for A that we can find. A could be, there are infinite possibilities for A, that would give us del cross A equals V, and V being this. So which means that we can set, so let us find an A with 1, 0 component. What I mean with this is that A has components AX, AY, AZ. We can choose one of them to be 0. For example, let's set this to 0. That is all right because as long as we can find an expression for A such that del cross A equals V. Okay, so say 1, 0 component, let's say AX equals 0. So this now becomes 0. So V, which is this, can be written as let's say let me write del cross A, where AX is 0. So I, this and this, so partial with respect to Y AZ minus partial with respect to Z AX, okay, plus J partial Z with respect to X, but that's 0. Okay, so that's 0 minus this partial respect to X A Z plus K, partial respect to X A Y minus partial respect to Y AX. Oh, by the way, AX is 0. Okay. So we equate this with this. That would give us, so for the ith component, x squared minus y squared equals partial respect to y of a z, partial respect to z a no, partial x y a z. This is a y. Okay. That would be this is a y. It's partial respect to z a y. Okay. So this here minus 2yz, that would be this, or 2yz equals partial with respect to x of a z. And finally, z squared minus 2zx equals partial respect to x ay. Okay. We can then integrate. So this involves only one partial derivative we can integrate. So we integrate. We find az equals, so we integrate with respect to the x. So we take the integral dx. So that would be 2yzx plus a function of y and z. Okay, let's call that f1. Similarly, ay, take the integral with respect to x. So that would be z squared x minus z x squared plus f2 y z. So to check, if we take the partial derivative of this az with respect to x, you get 2yz plus here, this is not the function of x, so this is 0. Similarly, here you have z squared minus 2zx. Okay, our next step is to substitute this to, so substitute az and ay to let's say if this is equation 1, 2, and 3 to 1. Okay, partial y, partial az with respect to y, that would be 2zx, and partial derivative fy. So you have here x squared minus y squared equals this with respect to y. So 2zx plus partial derivative f1 with respect to y. Okay. And this one, partial derivative of ay with respect to z. So this becomes 2zx. Oh no, z squared x. This just cancel. So you have here partial derivative of this with respect to z, f2. Okay. Now f1 and f2 could still also be specified. These are all the general functions. We can also specify them, but these are related to each other. So suppose if we choose f1 equals 0, this is just our choice, then there's a specific value of f2 that should satisfy this equation. So if f1 is 0, integrate over all z, then you have not, let me write over dz. So you have f2 that would be equal to, so this 0, this here becomes x squared z minus y squared z, and this is x x z squared. So you have minus x z squared. X z squared. This would be x z squared. Let me just check this. This cancels. Y squared would be, let me check if we miss something. Okay, I think we missed something. Okay, this is a mistake here. These two are not supposed to cancel. Oops. This is z squared x, zx squared. Okay, my bad. That is my mistake. So this is z squared x, zx squared. Okay. So this is z, oops. Ay is z squared x minus z x squared. So here you get partial of it might be best here to solve first partial of f2 with respect to z. Okay, so solve here first partial of f2 with respect to z. So that, let me erase this first. Oops. So partial of f2 with respect to z, that would be f2, partial of, okay, yeah, that I did not mean this f2 here. Perhaps let's do this later. Okay. So before we integrate, let's do something first. So here, partial, let me squeeze something here. Partial of AZ with respect to X, this one, would be equal to 2YZ. Oh no, partial of AZ with respect to X is 2YZ. I even missed something here. No. Okay, partial of AZ with respect to, we want to use equation 1, partial of AZ with respect to Y. Okay, partial of AZ with respect to Y, that's 2ZX. Okay, plus partial derivative of F1 with respect to Y. On the other hand, we want to know, okay, this is a comma, partial of AY with respect to Z. So AY with respect to Z, you have here 2ZX minus X squared plus partial with respect to Z of F2. And then we plug that in here. Partial AZ respect to Y, that's this, minus partial AY respect to Z, that would be this. So what we are missing are 2ZX and minus X squared, which we should write as negative 2ZX plus X squared. Okay, so we forgot to write this. Oh no, we missed writing this. So here we can cancel terms. This and this would cancel. X squared and this would cancel. Okay, is that right? 2ZX. Okay. So if so if F1 equals 0, so if this is 0, then you have Y squared equals, before we continue, we might be missing something again. Let me just check our YZ. To YZX, and this is X squared Okay, I think I wrote something wrong again. X squared minus y squared. Okay, I'm looking at the wrong notes. This in the book is z. It's not supposed to be y squared. It's yz, but let's keep it this way here so that we can continue. Okay, so this will not be the same as what is in the book. So you have in the book it's yz. We'll use y squared. I miswrote it like this, so let's keep it this way. Okay, so if f1 is 0, you have y squared. This is 0 equals negative partial respect to z of f2. Oops. Okay, take the integral. F2 would be equal to negative 1/3 y cubed. Okay, so this is, let's say, one possibility. Okay, second possibility, if f2 equals 0. If f2 equals 0, then this is 0. You have y squared. Oh, it's even negative here. So I miss a negative. Negative. Okay, so this becomes positive. Okay, y squared equals negative partial respect to z of f2 y z. Okay, and this gives us f2. Oh no, f2 is 0. f2 is 0. So negative y squared equals, this is 0, this partial with respect to, okay, I think I missed this. It's a huge part again. This is with respect to z, and there's a negative here. Okay, so y squared, or f2, is simply take the integral with respect to z, so that's y squared z. That's it. Okay, to check, take the derivative with respect to z, partial derivative with respect to z, you get y squared. So this is first possibility, or one possibility. Second possibility is if f2, by the way, these possibilities are really possibilities, which means that there are infinitely many values of a that we can get. These are just a few. So if f2 is 0, then you have y squared equals partial with respect to y of f1. Okay. So in this case, f1 is simply, so it's just a function of y. It's negative 1/3 y cubed. Okay, so if f2 is this, you have negative 1/3 y cubed. So if we choose possibility 1, I, okay, possibility I, and possibility double I. We can choose either. We can choose, let's say we can set a value of f1. Let's say f1 is some value x, for example. Then f2 would also change. So f1 and f2 are dependent to each other. If you choose one, the other one would be something. And if you choose a different one, the other one would depend, so it would adjust to something else. So if you choose one, then f1 is 0, f2 is y squared z. We just substitute that to get an expression of a, say az and ay here. So a z that's equal to 2yzx 2yzx plus f1. f1 is 0. And a y, that would be z squared x minus zx squared plus y squared z plus f2. f2 is y squared z. Okay. And these are just the few things or few or one a that gives us del cross a equals v. So a is, you have z squared x minus zx squared plus y squared z. Oops. This is the ith component plus 2y zx is the jth component. There are also infinite other possibilities. Okay, one of them if we choose this.